Hello everyone and welcome. Today is a very exciting day because I will be showing to you the progress made on the library code. Today I actually implemented the R classifier in the Mnist Data Set, and yeah. So for those of you that don't know, the Mnist Data Set was kind of the data set used for machine learning problems, especially in the early 2000s. Now we have more difficult problems that we solve, like CFAR and whatever, but MNIST was the data set, and it was quite a revolutionary one to kind of put different algorithms against each other and see how they held up. So this data set was by Yann LeCun and Karina Cortes and Christopher Burgess, and yeah, so it's 10,000 testing images and 60,000 training images. And they are 28 by 28 grayscale images of numbers. So a very small kind of feature vector for what we were used to now. But obviously, this was in '98, so obviously machine learning was not a technology we had today, and obviously the computers were not as strong as we have them today. More interestingly, we'll be looking at this neural network section. And what I've done was I took this experiment here with 300 hidden units on the first hidden layer, and 300 neurons in the first hidden layer and 100 in the second hidden layer, and they achieved an error rate of 3%. If we go back, we achieved an error rate around 8.5%. So pretty close. I do have to say that I did not use the whole 60,000 training samples. I only used 10,000, and I have to say I only ran it for 400 epochs, not even. So I'm sure if I ran it on more training samples, it would perform a lot better. But at the moment, I just did not have the time to do it. I'll maybe put it on a VM and then let it run overnight, and then see how much better it becomes. So pretty much what I did was some of the code I borrowed from Arthur Mensch. It's public code on the scikit-learn. It's one of the scikit-learn kind of blog posts kind of things or tutorials. So all it does is imports the data set. It does some kind of permutation and shuffling. It then creates the actual splits, again 10,000 elements in the testing size. It scales it because it's good practice to scale, I guess. And then it does some more kind of reworking with the matrices, because for example the actual labels come as strings. Let's say we have strings 1, 2 and 4. Instead what we need is one hot representation of the strings. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this is the one hot representation. So what we want is a matrix like this. Then this would mean 1, because this is 0, then this is 1, 2 and so on. So this is 2, and then this is 0, 1, 2, 3. I can count 0, 1, 2, 3, 4. So this would be, so we want pretty much a function which sends this vector to this matrix, and this is what this is doing. And this is obviously because our library does not support labels like strings at the moment. It's not an insanely difficult thing to support, but as of now it does not. So I just did it here. Then I created a neural network, again 300 neurons in the first hidden layer, 100 in the second hidden layer, and then again here I hope you can appreciate how readable this neural network API is. The input size is 784 by 784, which is 28 squared, because these are you can think of it as like 28 pixels in this direction, and then 28 pixels in this direction. So let's see if I can draw it like that. So it's 20 by 28. So obviously what we're doing is we are kind of taking the matrix and turning it into a vector by just stacking the rows, right? Or whatever way around you want to do it. And then that's what we're doing. Then we're fitting it to the training set, and then pretty much this matrix, what it will do, and then I'll show you an actual example here, the images. What this matrix will do is it will spit out like a random, like decimals, right? Well, not random obviously, but it'll spit out some decimals, and then what we do is we consider the highest output, the highest positive output, to be the right one, right? Because we're not using actually, maybe I was planning on implementing it, but I didn't get around to doing it, so a softmax layer to turn them into a probability, but maybe later on. And then what we do is just simply look at the accuracy. In this case, as almost 91.5%, and then it will, and then I just save it. I pickle it down to this file. That's about it. So for this, and now let's actually look at the cool stuff. So all I do is in this notebook is I just import some libraries, import the functions which I've shown you before, and then pretty much what I do is, again, here I'm not scaling it because if I scale it, these images look worse, but the classifier still works regardless, so that's fine. And then what I'm doing here is I'm just getting 5 examples from the testing set, and then I load the classifier which I've trained here, which is this classifier here, and then I show the predictions, like the raw estimates, and then the actual prediction, and yeah, so this is the result. This is the testing set image of a 5, and it's obviously the true label is a 5. These are the raw estimates. So as you can see, it really doesn't think it's a 0, a 1, or 2, or a 3, a bit more, a 4, a bit more, a 5 it's pretty confident on, and so on. So it's pretty confident it's a 5 relative to the other values, which is quite good. A 0, again, extremely confident that it's a 0 compared to the other values. Obviously you can see that it does kind of all add up to 1, because again, in our training set we're doing this one hot representation, so it will be close to like a kind of what you would expect from a softmax layer, but obviously it's not, because there's negative values and this does not add up to 1. Showing image of a 1, and again this thinks it's a 1 with pretty high confidence. Again, a 9, you get the point. A 9, it's again pretty high confidence. A 4, it's very, very high confidence. So as you can see, this seems to be working exactly as expected, which is quite nice. I'm really new to these notebooks, and I don't know. So as you can see, this is exactly as you expect. The classifier is working correctly. I will maybe train it for longer at some point, because I've seen here that they've done this 800 hidden unit network, and it seems to be working a bit better than this. Oh, they even did like bigger ones here. Okay. Well, anyway, I did like kind of like the smaller deep learning one. I just wanted to do the deep learning one because I just thought, I mean, we're building a deep learning library, might as well do the 3-layered one instead of a 2-layered one. So yeah, I mean, I'm not really too fussed about the exact performance. I don't want to really, I don't really care that much, as long as it kind of works. The idea now, what to do with this is, I'll be showing you how to build an API for this. So we have our classifier, which is trained to this pickled file, which I cannot see here. So it's on this file. What I want to do is show you the actual web API, how to build one, how to go about maybe making a website which actually uses your model. So what I will do is I'll have like an HTML page where you can draw a number, and then it will send a request to the web server. The web server will then pick it up and then maybe send it to the API if I want to decouple them, but maybe I just won't even bother to decouple them. I'll just have a simple web server, right? Because I can't be bothered to write a RESTful API for this, but maybe I can show you how to do it. Then maybe if you're interested, I can Dockerize it, show you how to productionize it and stuff along those lines. I think that would be interesting. But yeah, so for this video, this is all kind of what I wanted to show, just this classifier working on MNIST. There's some changes which I'll push to GitHub, and then maybe you can check them out in the repo, which is in the description. And yeah, hope you enjoyed the video, and see you next time. Bye bye.